Hi folks, welcome back to Physics with Captain Rod. This video here is intended to be example 2 of finding the frequency or the period of a vibrating system. So what we're looking at here, we're going to imagine this disc-shaped geometry with mass m, radius r. It's connected to a spring of force constant k at the position shown. This position is going to be considered to be the equilibrium position. We're going to imagine now that this point is pulled over here a distance and released. Now what's going to happen, assuming this thing rolls without friction, is that this thing will now oscillate back and forth. So like this point, which I've got shown over on the right, is going to basically do this as this system rolls back and forth. I'm going to use this angle theta here to describe the orientation of the disk. So right now we're going to want to think of this theta as a generic theta, a time-dependent angle as this thing rolls back and forth. All right, so let's do it. So similar to the previous video, first step is we have to write out an equation for the total mechanical energy of the system. So as this thing is rolling at any given point, it's got a kinetic energy equal to 1/2 mv squared for the translational motion of the system, plus 1/2 I omega squared for the fact that this thing is rotating. Now the way that I've got this expressed, this I would be about G, the center of mass of the system. Now, we could leave it like this, or we can express the kinetic energy with one term, a rotational term, if we find the I about the instantaneous center of rotation. So the instantaneous center of rotation for this object is here. It's rolling basically about that point. So what I'm going to do is I'm going to go back, and I'm going to go ahead and do that. I'm just going to express the kinetic energy as 1/2 I omega squared, but this I needs to be about this point right here if we write this equation with one kinetic energy term. Right? Potential energy terms. Well, this thing's rolling back and forth. The gravitational potential energy is not changing. I can go ahead and just put a datum right through here and call it 0. However, we do have a potential energy stored in the spring. Elastic potential energy is 1/2 k, I'll put d squared for a moment, where the d is the distance that the spring is compressed or stretched, depending on the case. In our particular problem here, that distance is approximately equal to this, which can be expressed as r times theta. So I'm going to go ahead and go back and put r theta squared for the kinetic energy, or I'm sorry, for the elastic potential energy stored in our spring. All right, next. All right, we've got an equation here. It's got thetas and omegas in it, but it doesn't have time information. So I can change this equation to a time-dependent equation by hitting it with a time derivative. Before I do that, let me go back and just point out one thing. This system, when we think about the forces, we've got a gravitational force down. Go ahead and just draw these quick. We've got an elastic force. You know, I really should draw the free body over here. Gravitational force down. This spring is now applying a force basically like this on that object. And we have a normal here at this point and a frictional force, which is probably something like this. An important thing to realize here, the gravitational force isn't doing any work. There's no displacement vertically. The spring force is doing work, but we're taking that into account with the potential energy. The frictional force we don't need to worry about. This is rolling friction, so there's no work term for that frictional force. I think I have them all. You always want to consider all forces acting on a system when you're thinking about work. Now, because there are no non-conservative forces adding to or taking energy away from the system, when we time differentiate this, which is going to be the next step, that left-hand side is 0. Energy of this system is constant. Okay, time derivative of this term. So the moment of inertia is not changing. When we bring down the 2, that's going to become a 1 times I times omega times the time derivative of this, which would be omega dot, plus. All right, what do we got going on here? This 2, time differentiating, that's going to become a 1. K r squared theta to the first power times the time derivative of theta, which would be theta dot. And I think that's it. Okay, let's look this over here now. This theta dot and the angular velocity are the same thing, so these actually go away. This term, remember, the angular velocity is theta dot, so this is a theta double dot. So this equation rewritten is going to be 0 equals I theta double dot plus kr squared times theta. Next step. We want this thing highest derivative first with a 1 in front of it. So we're going to want to divide by the moment of inertia. So this is going to be theta dot plus kr squared over I, the moment of inertia, times theta equals 0. All right, so now let's start thinking about this I here. Moment of inertia, this moment of inertia needs to be about this point. So I'm going to start with the moment of inertia of a disk about its centroid, or its center of mass. That's 1/2 mr squared. Now, applying the parallel axis theorem, we're doing rotation about this point, so we need to tack on an mr squared for the fact that the axis is moved from here to here. So what we get out of that is 3/2 mr squared. So this equation, theta double dot plus kr squared over I, well, the moment of inertia here is 3/2 mr squared, so how about we do this? 2/3 mr squared, because when we divide by 3/2, that'd be the same as multiplying by 2/3, and then times theta equals 0. Okay, so the radius went away. Apparently this is not dependent on the radius. So we got theta double dot plus 2k over 3m times theta equals 0. All right, and we're ready now to solve for the angular frequency. So equations of this form, second derivative first plus the function back again, a constant times the function back again. This has sinusoidal solutions. So the solution of this equation can be expressed theta equals a sine omega t plus b, plus b cosine omega t. No initial conditions given in this problem. It's not important for the angular frequency, so I'm going to throw out the cosine term and choose to keep the sine term. I'm going to need a little more room. All right, so in order to find the frequency, we have to solve into our differential equation here. That means I'm going to need the second derivative of this animal. First derivative is a omega cosine omega t. Second derivative is minus a omega squared sine omega t. Now we're going to take this animal and sub it here. I'm going to do this sine omega t plus, did I say here, I'm working with this equation here, 2k over 3m times theta, which is a sine omega t, equals 0. Okay, same as the last example. You can factor out an a, you can factor out a sine omega t, and you are left with minus omega squared plus 2k over 3m equals 0. Same argument as last time. If a were 0, you wouldn't have a solution left. Same thing with a sine omega t. So if this equation is equal to 0, that's the part that we want. So the angular frequency is going to equal the square root of 2k over 3m. And remember, this is equal to 2 pi times the frequency of the system. So that's good enough. Basically, there we are right there. We have an equation here that tells us the frequency of the system. You notice that the frequency depends on the spring constant and the mass, and hopefully this makes sense. Stiffer spring, this thing will vibrate back and forth at higher frequency. Larger mass will actually drop the frequency. So again, the purpose of this video is to help demonstrate how to find the frequency of a mechanically vibrating system. It's very similar to the last video. You write out an equation for the total energy of the system. Assuming there are no non-conservative forces acting on the system, then the total energy would be constant. So when you hit this with a time derivative, you'd get a 0. Then you time differentiate the rest of it. Put it in standard form, which is highest derivative first with a 1 in front of it. Equations of this nature have harmonic solutions, which look like this. If initial conditions are given, you would typically apply them. If not, pick your favorite function, sine or cosine, and calculate the second derivative. Sub these two things into the original differential equation. Solve for the angular frequency. Hope this video helps. Have a great day.